Welcome to the Explainer. Today we're taking a complete inside-out anatomical journey through computer hardware to help you absolutely crush your IGCSE exams. Specifically, we're going to unpack the entire Unit 3 topic on hardware. We're breaking down everything from the microscopic chips processing your data right down to the massive sprawling networks connecting our world. So let's jump right in. Here is our roadmap for today's Explainer. First, the brain, or CPU architecture. Second, boosting computer performance. Third, input and output devices. Fourth, memory and data storage. And finally, networks and embedded systems. Starting with Section 1, the brain, CPU architecture. To really grasp how modern computers actually work, we absolutely have to talk about the famous von Neumann architecture. This brilliantly illustrates how the CPU, memory, and input-output devices are all seamlessly connected. And they're connected by buses. Think of these buses as the computer's central nervous system, transmitting data everywhere it needs to go. You've got the address bus carrying signals one way to find specific locations, the data bus moving the actual information back and forth bidirectionally, and the control bus basically managing the whole operation. It's just this beautifully orchestrated system of constant communication. Now, deep inside that CPU, we have something called registers. Honestly, the best way to think of these is like a master chef's immediate countertop space. They hold the precise instructions, memory addresses, and data the CPU is actively calculating right this very millisecond. For instance, the IMAR, or memory address register, holds the exact location of the data. Meanwhile, the accumulator temporarily holds the answers to active calculations. The other registers, like the program counter, the CIR, and the MDR, handle the specific tracking, the instructions, and the raw data packets moving in and out of the processor. So to actually process information using that countertop space, the system relies on what's called the Fetch-Execute cycle. The program counter tracks the very next move. Then the CPU fetches the command from memory, brings it to the registers, decodes exactly what it means, and then executes it. And the crazy part? This entire cycle happens millions of times a second in a continuous rhythmic heartbeat. Moving right along to Section 2, boosting computer performance. Okay, so how do we actually make this brain run faster? Well, you can boost processing performance in three main ways. First, by increasing the clock speed. That essentially synchronizes operations with a much faster internal metronome. Second, by expanding the ultra-fast cache memory, located directly inside the CPU itself, which means it doesn't have to waste time fetching data from the main memory as often. And third, you can literally stack multiple processor cores together, like upgrading from a dual-core to a quad-core setup. But wait, here's a crucial point you definitely need to remember. You'd think an octa-core would just automatically be incredibly fast in every scenario, right? Well, no. More cores don't magically equal faster speeds across the board. Because as communication between all those different cores increases, data traffic across the cables gets super heavy. If the software you're running isn't specifically designed to use all those cores efficiently, that extra traffic can actually bottleneck your potential performance. All right, Section 3, input and output devices. Let's zoom out from the processor for a second. How does the computer actually sense the physical world? It uses sensors. Whether it's acoustic, accelerometer, flow, gas, humidity, infrared, light, magnetic, moisture, pH, pressure, or temperature sensors, they all act as digital senses. But here's the catch. Computers only speak digital, just pure ones and zeros. So all that physical data absolutely must be sent through an analog-to-digital converter, or ADC. That converter translates the messy physical world into a language the microprocessor can actually understand and use. Now on the output side, let's talk visuals. Projectors are a major topic here. You really need to understand the distinction between an LCD projector and a DLP. An LCD projector works by passing a powerful beam of light through three separate red, green, and blue screens, giving you great color saturation while running cooler. A digital light projector, or DLP, on the other hand, relies on literally millions of tiny micromirrors on a chip, rapidly tilting toward or away from a light source. This setup makes them smaller, lighter, and generates incredibly high-contrast images. Which brings us to Section 4, memory and data storage. Now that our computer can process and output data, it obviously needs a place to store its experiences. Starting with short-term memory, or RAM, we basically have two main players. There's DRAM, or dynamic RAM. This consists of transistors and capacitors that require constant refreshing to hold on to data. But the upside is it's cheap and offers high capacity. Then we have the much faster SRAM, or static RAM. SRAM uses flip-flops and doesn't need that constant refreshing. Because SRAM is so incredibly fast, it's typically what gets used for the CPU's cache memory. We've all been there, right? You open way too many browser tabs and your RAM completely fills up. If your immediate memory countertop gets totally overwhelmed, the system smartly prevents a crash by creating virtual memory. It essentially borrows a chunk of space on your secondary storage, your hard drive, and temporarily pages idle data over there. This frees up your active RAM so you can just keep on working without everything freezing. Speaking of the hard drive, what about the really massive long-term storage in the basement? Well, older magnetic hard disk drives, or HDDs, which use spinning platters and actual moving read/write heads, are rapidly being replaced. Solid-state drives, or SSDs, are completely taking over. Why? Because they control the movement of electrons within NAND chips. SSDs have literally no moving parts, they run much cooler, and they provide lightning-fast data access compared to the old spinning disks. And finally, we arrive at Section 5, Networks and Embedded Systems. Let's talk about how all this hardware gets totally miniaturized. Embedded systems are exactly what they sound like. They are tiny, specialized microcontrollers built directly into everyday devices. Think about your washing machine, your microwave, a GPS, or a security system. They run on a highly specific combination of hardware and software dedicated to doing just one single task perfectly. They require barely any power and are incredibly cheap to manufacture. Though, fair warning, they are notoriously difficult to upgrade once they're built. Now, for any of these devices to actually socialize on the internet, whether you're talking about a high-end laptop or a smart fridge, they require a network interface card, or NIC. This card comes factory stamped with a permanent, completely unchanging 48-bit MAC address. That is your hardware's unique physical fingerprint. You also need a router, which sits on your network and basically acts like a traffic cop, determining the absolute most efficient path to direct data packets to their proper destinations. Here's something absolutely wild. To accommodate all these devices, we are currently going through a massive transition in IP addresses. For decades, we've relied on IPv4, a 32-bit system that gave us about 4.3 billion unique addresses. Which sounds like a lot, but with smartphones, smart TVs, and all those embedded systems coming online, we literally ran out. So we are shifting to the massive 128-bit IPv6 format. Just to put that in perspective, IPv6 provides roughly 340 undecillion addresses simply to accommodate the global explosion of connected internet devices. Which leaves us with this final thought to wrap up our explainer. Take a look around your kitchen, your living room, or even your classroom right now. Think about the von Neumann architecture, the sensors, the RAM, and the network cards we just unpacked. How many hidden computers, embedded systems, and active IP addresses can you spot operating silently all around you? Keep that in mind as you prep for your Unit 3 exams. Thanks for joining me on this deep dive into hardware.